Hello, good day for you all, and welcome back to my channel. And this time we want to discuss about hydraulic machine mechanism and the in systems. And for this discussion, we gonna have some steps. The first step is a very basic calculation, what we call it a mechanical calculation. And the second step is equipment sizing. Yeah, and the third step is CAD 3D using SolidWorks examinations to explain some critical parts that might raise in your minds how its actual working principle, so for us to more understand what actually inside. And the fourth discussion is will show you uh, what insights one of the critical equipment of directional valve to have a feeling how it looks like. Yeah, so the first step, as I mentioned before, we will do a kind of a mechanical calculation. Before doing kind of these mechanical calculations, of course we have to adopt what machine we would like to design. So actually this is as a final step of the machinery. Yeah, the final design, but to have a feeling with you how the machine and the objective of this design as shown is in this 3D drawing capture. So this machine, I call it a SMAT for press machine. SMAT is a single minutes etching dice. Yeah, to help the operator there or the technician to set the mold before installing it to real machine. So it's kind of SMAT, because if installing in the real machine directly, it will takes more times. Yeah, so before installing that mold to the machines, we have a tandem mold that if the first mold already tears, yeah, so we will use this tandem mold directly to the machine, but this tandem mold already set in separate machine, that this machine we call as SMAT hydraulic machine. So the working principle is very simple. These machines, the table here will be moving up and down, the mold here and the setting jig here. That's it, very simple. But these very simple ones, if we don't understand the basic of mechanical in designing, sizing and etc., then will create problems. I have experience before, just now experience months ago, last year I think. There is a mechanical engineer who designed something by feeling only, without mechanical calculation. Yeah, and then they ruin the project and have to stop that project. And I remember suddenly, I remember in the past I made some simple of hydraulic machine, and I did calculation for that. So this is back to the first one, the calculations, mechanical calculation, the very basic one. So as you can see in this free body diagram, we back to the university times, that the machine, the table will be moving up and down. Okay, so I have a data the mold around 100 kg, and the frame I estimate, and I will make it no more than 129 kg, and I have a total mass of that system. Yeah, so according to the formulation of the newtons, yeah, that if you want to lift it up, yeah, so the sigma force will be equal to mass and its acceleration. Okay, and then below it, the formula again, you have power needed force needed to move it up, but as in opposite direction you have the weight of its total mold and that frame. And then by formulations, then you need this force, yeah, to lift that tables. So when it going down, of course it will be less, because the direction of um, weight force is same with the force needed. So actually the force needed is will be less, but we will, of course, as a mechanical engineers, we concentrate our times and our calculation based on the heaviest one. So this is the heaviest condition, yeah. So based on that formulation, yeah, we go to this calculation, yeah. So the force needed for that case around 2.2 kilonewtons, and the power needed, yeah, around 225 watts. So power is calculated based on the force and the velocity units. In this case, the velocity I need is 0.1 meter per second, and the acceleration 0.1 meter per second square. And then I have a safety factor for that. Usually mechanical engineer use a 1.5, 2, or etc. But in this case, I made a 1.5 safety factor. So at the end, I have a new force needed to counter this load around this number 3.3 kilonewton something, and etc. So from this very basic calculation, then we have to calculate and size the equipment for that. So as you know, we have a hydraulic here. We call it actuator, cylinder actuators, hydraulic, that two acting up and down. And I go to the catalog of that hydraulic equipment. I have a catalog here. I use Parker catalog, this one, yeah, Parker catalog. The stroke I needed, of course, I based on the travel I need, yeah, and etc. And then from that point of view, and then we came with this solution. I need Parker with the bore diameter 3.25 inch, and then these models able to sustain until 3000 psi, yeah, around if you divide 14 3000 is around 200 bars absolute, yeah. So I got that sizing back again to the actuator cylinder. So I choose this model, yeah, double acting, 2 hole here, yeah, just to have a view in the CAD. It looks like this. I deliberately make this transparent just to see what the meaning of double acting. It means you have 2 ports. When the oil flowing to this directions, the oil will be back to the tank, and then the power of hydraulic motor transfer to here, okay, and then the table finally can be moved up, okay. So back again to the calculations. So now we are in the best equipment calculation. So we are sizing the equipment. So in sizing the equipment, we have to work with the catalog. You cannot more working like a mechanical calculation. This is very theoretical. So you have to more to see the catalog, whatever the catalog, Parker, Eaton, or any brand you want to see. So after you sizing the cylinders, and then you go to the hydraulic pumps, yeah. So hydraulic pumps, the sizing is based on the speed you need when it travel up, and then when it travel up, and then the you choose the size of this cylinder actuator, then you have a flow rate needed to have that kind of speed. Okay, so we lock down that things. So I need 23 liter per minute, and the pressure needed, it's of course based on the force here, yeah, multiply by the area of the cylinder. But in this calculation I make safety factor 1.5, so I need around 8.7 bars. It's very small if in the hydraulic system, 8.7 bars. So now I need to sizing my pump. Again, sizing the pumps, you have to see the catalog. Okay, in this case I use Eaton. Yeah, previously it's a Vickers and then acquired by Eaton's. This is a fan pump. Yeah, kind of a gear inside. It's not centrifugal because it's a high pressure, a bit high speed. So fan pump is the correct pump for this. So if we go to the seat of the fan pump here, hydraulic pump, fan pump, this is the pump looks like in the catalogs, and I even redraw the pump, yeah, based on their catalog. If we go to this 3D drawing, this is the pump. Okay, this is the pump, and then if you see the, okay, by the way, I did this five years ago, I think 5 or 6 years ago, in previous company I work here, when I was national engineering and project manager there. So one of the things of my jobs, yeah, to provide solutions or to design machines to kill the waste, yeah, is because this also SMED, single mean exchange dies, is also proposed to kill the waste, and then to maintain the machine setting is good when we make the products. Yeah, okay, this is the pump. So back again to the catalog and the calculation. Of course you have to download the catalogs and learn from that. So in this case I already prepared that based on what we need. So what we need is around 23 liter per minute. So we go to the hydraulic pump chart. It has a two common chart. First, the flow and the speed. Yeah, because it's a fan pump, and based on the similarity calculation, is the speed is linear to the flow. So in this chart you can see around 23, let's say here, and then we need speed around 2800 from this model V10. Yeah, and the pressure, I don't need pressure so much, only around 7 to 8 bars. So but I put in this location, yeah, it could be maybe only 7 bars. And then after that I move to the right chart, what we call power chart. So in this power chart I need around 23 liter per minute, or around, let's say, 6 or to 7 US GPM. And then in this graph it has around 7 US GPM and then 100 psi. But 100 psi is not enough, because we need around 160, around 9 bars, yeah, psi. So it's around here, yeah, it's around here. So we need power around 2 kilowatt. So the pump requesting power input to the pump, yeah, to have this flow and this pressure around 2 kilowatts. Okay, so back to the calculations. So I choose 2.2 let's say 2.2 kilowatt based on the charts. Okay, and then flow 25, and the rotation is 2800 something. That's the pump. So now how to drive this pump, because the pump needs this 2.2 kilowatts, yeah, to generate 25 liter per minute, and the pressure about 9 or 10. Yeah, so we go to this. Yep, we go to this. Of course, when we go to this, we all have to talk about the always about the catalog. So let's see AC motor here. I have a Teco AC motors, so I choose this. Yeah, RPM 2800 something, and the power is 3 kilowatt. I make a safety again. I make a safety compared to actually needed. It's a small safety. So then from that point, if we compare, is our motor is higher than it needs. Yeah, okay, so this is already equipment sizing. When we talk about equipment sizing, please, you have to work with the catalog. Okay, and then directional valve. Yeah, for you, I also redraw the directional valve in the CAD. Yeah, this is the directional valve. Okay, to manipulate the direction of the fluid. Yeah, if we go back also to the schematic, this is the directional valve. Yeah, to manipulate when it's unit up and when unit down as well. Yeah, this directional valve, of course, the input needed first is the pressure and the second is the flow. So we go to the directional valve chart. I use here directional valve Yukon. Yeah, if we go there, so I choose this one with the 100 liter per minute, and then pressures around here around 35 bar is very high. Yeah, very very good already. Okay, because I only need around 23, yeah, liter per minute, and the pressure around 8. Yeah, in case maybe you don't follow this, then if you choose the smaller directional valve flow capacity, yeah, of course it will wrong. Yeah, you will not meet your expectation to have that cylinder or actuator moving with this 0.1 meter per second. Yeah, so that is why you have to see the catalog, what its performance said. Yeah, previous experience, my mechanical engineer only sizing things based on his feeling, not follow the calculations. Yeah, and then the result is terrible. Yeah, so in this case, use general formulations for what system you have. We call it mechanical calculations. It must be correct at the first place with the all assumption insights, and then equipment calculation and sizing. That's very important. Okay, so we already have these two things. Yeah, we already have these two things, and then from these two things, then we will go to design the CAD using CAD 3D CAD. But in this example, I reverse it. Yeah, but actually I did it submit waiting for the calculation, and then redraw to the CAD and reverse again. Yeah, so in this CAD I use SolidWorks. Yeah, this is the tank, this is the pump. Okay, and then this is a linear bearing, and this is the solid shaft, and this is the hydraulic, and we have a proximity sensor here, 3, bottom, top, and then safety. Yeah, top safety. Okay, and then we have a push button here for up and down, and of course emergency switch. And we have a small control panel here with the isolator switch. Yeah, when you need maintaining the pumps, you need to isolate the energy. And then one of what important things maybe you need to know how the pumps connected to this AC induction motors is using a gear. It using a gear coupling. It's not flexible coupling because the torque is quite high. Yeah? So I make this a bit transparent. This is what inside. Yeah. If we check furthermore, if I hide this, this is a gear, and this is a kind of rubber. Yeah, if I put this transparent like this, yeah, so that's very common because high torques. And then also to minimize the fatigue of the shaft, that is why they put the rubber there, rubber joints. Yep. Okay, and then this is a very common product. Yeah, very common product. Only this flank that connected you need to fabricate. So that's it about the general guide to design the hydraulic system. Very simple, but don't forget one thing, that it should be engineering solutions from sizing the equipment. So you have to work with the catalog, whatever brand you want to choose. But personally, I like Eaton brand for the pumps, and then for the hydraulic actuator I prefer Parker. For the directional valve I prefer using Yukon. But again, you have to back also to the budget you have. Yeah, that's the two sessions already covered. The third session and the fourth session we will continue, because the third session will be very interesting for you. That question, I have someone that question, how is manifold look like inside. uh, I will answer that for the second session. And then also I would like to open what inside the directional valve to more understand. After that, I believe you can do that by yourself and enhance your ability to design and to calculate the simple hydraulic mechanism system. Okay, thank you very much. See you at that next session.